So without further ado, I will introduce our final talk of the day, and this is going to be around the Connected Everything Network Plus and digitalization, digital technologies for intelligent process monitoring. And it will be provided by Debra Fearnshaw, who's a project manager at the University of Nottingham, and Nick Watson, who's an associate professor in the Faculty of Engineering, also at the University of Nottingham. So I'll hand over to you guys now.
Thanks, Tom.
Thanks, Tom.
Great. So hi, everyone. I'm Debra Fearnshaw, and I am the network manager for the Connected Everything Network. So I'm just going to talk a little bit about that before handing over to Nick to talk about some of his research. So Connected Everything is an EPSRC funded Network Plus, and actually we're really lucky because we've been in the second iteration of Connected Everything so far. Connected Everything actually started in 2016, and we did the first 3 years, 2016 to 2019, and we were lucky enough to be given funding for an additional 3 years to continue until 2021. So we've had lots of opportunity to get new members registered as part of the network, and currently we have around 400 members registered, representing well over 100 different institutions, companies and organisations. While the network is very much about about engaging with industry, we do have a lot of multidisciplinary representatives across the network, of some of which are on screen now, from many different facets of the world of digital manufacturing, and we're really pleased that we try and represent as much of as many of those academics' interests as possible across the network. Next slide, please, Nick. Thank you. So how do we support the future of digital manufacturing in the UK? Well, from this slide, as you can see, we look at many different aspects of that, and we really try and bring it all together to make sure that we do have a strong people and skills focus for what we're doing. And I think the next slide will go into more details about how we do that. We also have lots of cross-disciplinary activity as well. So in terms of what we actually do, we have a very strong focus on feasibility studies, and part of that is to make sure that we're really offering early career researchers the opportunity to develop their skills and research in the area of digital manufacturing through developing feasibility studies. And we're really pleased that often the studies are actually generally they can be risky, and we like to take positive risk to give people a real opportunity to do something new. Already in Connected Everything, we've already had 2 feasibility study calls. We had one that concluded in February this year, and we've done another one in July this year. We're now pulling together our 3rd feasibility study call, which we're hoping to launch in early 2021, which will be focused on the themes that we've recently revisited in our thematic areas. We now have 7 themes that cut across all our activities, which we think really help focus people's minds on some of the challenges in digital manufacturing coming out of the comments that were made in our summer conference, and also some of the feedback that we've had during the pandemic as well, and how we can really make sure that we're contributing to efforts in that respect. We also are very keen to look at the future as well, and one of our key outputs that we're looking to develop is our Digital World 2050 report, which will be really looking at the future of digital manufacturing and how we can contribute to that and really identify some of the challenges and perhaps what some of the solutions are. We are also keen to support early career researchers in a number of different ways through our People and Movement and Skills strand. So we were really pleased to host a summer school this July. Obviously, it was entirely online, but it was a really successful summer school with 25 participants across the UK being able to join us, and that was looking at how cobots, collaborative robots, might be able to address some of the issues in a post-pandemic COVID world. We're also still looking at how we can support placements as well for early career researchers. Obviously, as the name suggests, we are a network, so conferencing and networking is really key to what we do, and we're continuing to do that. One of the most recent things that we've tried to do to ensure that particularly early career researchers can access, the network and get that advice and support that they need is by setting up a LinkedIn group. Most recently, which is starting to have some good membership there. Everything that we do in Connected Everything we like to share, and we do that via our website, where we really try and ensure that the learning, whether it's from the feasibility studies or any of the work we're doing, is shared widely with the community. Also, recently we were able to get a knowledge and research exchange lead on board, who's really helping us ramp up our dissemination and impact work. So in terms of Connected Everything 2, we're really focusing on accelerated digital manufacturing research, collaboration and innovation. And we're looking through doing that through a number of strands, which are, if you could click away, Nick. Brilliantly, working directly with the catapults, linking with the knowledge transfer network, working with our industry groups, and one of the ways that we're doing that is we're actually focusing at we've got a couple of opportunities at Digital Manufacturing Week next week, where we're really hoping to get some insights from industry leaders through those events. And also we're looking at delivering events that offer new opportunities to develop new partnerships. So the thematic areas, which I just recently mentioned, we've just done a really good review of these. This was one of the key outputs that came from our conference in July, where we really asked our members to have another look at our themes and make sure that from what we thought was right when we were starting to think about Connected Everything to where we are today, that they're right. So now we've gone through that refresh process, and we're really pleased with the 7 themes that we've got, which we think really do capture what's important to digital manufacturing at the moment. And in terms of the outputs from the thematic areas from the first round of Connected Everything, they helped to support some of the Industrial Strategy Challenge Fund Made Smarter proposal. So we're really pleased to see that they were embedded in that work. And again, these themes that we've now come up with are looking to influence our 2050 work on the future of digital manufacturing. So does this link work? This is an example of one of our feasibility studies that we funded back in February. And we think it's really interesting and hopefully gives you a taste of some of the things that we're doing in Connected Everything. Have we got sound?
Sorry, can you guys not hear that?
No.
Okay. I think we'll have to skip on then. Sorry about that.
That's all right. I thought it was just me. Not to worry. We tried. Yeah. What I'll do is, while Nick's doing his presentation, I'll put the YouTube link in the chat. So if anyone wants to have a look at it, then they can look at it via the YouTube link. So no problem there. What we think the benefits are joining of the Connected Everything network is that you're joining a really wide and diverse pool of knowledge. As I say, we've got nearly 400 members in the network, and that represents a huge amount of different subjects, really across many areas. So we think that that's really important for people to kind of like come together, share their knowledge. We also fund feasibility studies. As I say, our next call is going to be early next year. And one of the things that we really encourage in the feasibility studies is we're really happy to see novel ideas. That's something that's really interests us. And also we really do want to see that connection with industry as well. So if 90% of our feasibility studies have had SME partners, and we think that's really important, even though it might be very early stage research and early thinking, as feasibility might suggest, it's really important for us to make sure that industry, the link to industry, is established even at that early stage. We also have had a track record in influencing policy. Again, as part of our feasibility studies, we also offer mentoring to all those teams. So we really do encourage early career researchers to take a lead in the feasibility study. And as part of that, we do offer mentoring. And on top of that, we are also thinking about how to pilot a mentoring opportunity for any early career researcher wanting to come, wanting to explore that and kind of like develop their career with perhaps someone with more experience. We want to develop collaborations, and again, we can help people find people through the network. So again, if there's an area that you're working on that you think might need some digital manufacturing expertise, we can help make that happen. And also, obviously, in terms of knowledge transfer, everything that we do, we share through our events, our websites, and through our conference. So last final plug for me, really. If you want to join Connected Everything, then please just go to our homepage and look for the nice yellow box that just says join our network. And it's a very simple form which to complete, which means that we can get in touch with you and we can share with you our newsletters, our emails, make sure that you get in touch with the people that you would like to in order to progress your work and research. Thank you.
Thanks, Debra. I think it's worth saying that when Tom got in touch, we were really looking for a talk in the formulation space here, but unfortunately we haven't funded any feasibility projects yet in that area. So I think this is my kind of call to everyone who's on this event today. If you're interested in formulation and you've got a good idea and it's suitable for a low TRL feasibility project, please consider applying. And as Debra said, just join the network. You'll get a newsletter and you'll get all the information on that. What I'm going to give you a bit of talk about is the research that I performed, my group performs. And actually, we had a feasibility study from Connected F4.1. So I'll talk a little bit about that, and then I can probably explain what's happened after that and how it's been really beneficial to my career. But once you've come up with this fantastic formulation, one of the things you have to do is actually start making it. And when you're making it, there's lots of opportunities for digital technologies to monitor these processes, control them, and optimize them. My group, we're really interested in digital technologies and digital manufacturing, but within the food and drink sector. We do look at some of the other process sectors, fast-moving consumer goods, pharmaceutical, oil and gas, but mainly food and drink. And we work a lot on sensors and online data analytics. And today, what I'm going to talk about is how we can combine the in-process sensors and techniques such as machine learning, deep learning to monitor processes more effectively. We work a lot with ultrasonic and optical sensors, and we do some interesting work of combining the two through multi-sensor data fusion. And really, the whole purpose of our work is to try and improve the sustainability, safety, and productivity of these manufacturing processes, because there's some huge challenges. If you look at the types of resources used by the food and drink sector, and the types of emissions, they're massive, and all the safety concerns around, for example, allergens. So we try to work in that space. We're also very interested in appropriate technologies for SMEs, so low cost, easy to use, because within food and drink, we always say it's the biggest sector, biggest manufacturing sector, but it is dominated by SMEs, and we need appropriate digital technologies for these. So today I'm just going to briefly talk around this concept of combining low cost sensor data and in-process sensor data and machine learning predictive analytics, and talk about some of our experiences and methodology we use. And then I'm going to focus on 3 case studies. I think it's worth looking at this. As Debra made reference to the Made Smarter report, and the Made Smarter was a report that came out, and then we've got one of the challenges as part of the industrial strategy. And this is really focusing on 5 enabling IDTs, so industrial digital technologies. And we've got the additive manufacturing, virtual reality, augmented reality, robotics and automation, and we've got AI, machine learning, data analytics, and then industrial Internet of Things. And industrial Internet of Things, that's really our data collection, these connected devices. And I've highlighted the AI and the IIoT, lots of acronyms there, because I think they're the ones that are really going to have the big benefit, especially within the sectors such as the food and drink. And I'll explain why. If we look at the food and drink sector, it's characterised by high volume, low value product sectors. It's different to specialty chemicals, pharmaceuticals. So they're very different investment models and very different time frames when looking at return of investments within those sectors. As I've said before, many SMEs in the sectors, lots of legacy equipment. So any digital technologies, we really need to look at technologies we can retrofit in a cost-effective manner. So some of the sensor techniques I'll talk about today, we're developing for around £1,000, and the data analytics, we can stream the data back to our lab, do that remotely. So again, that's low cost. But there is lots of challenges in the food and drink sector, and the main one is it's highly variable biological materials. If you're talking about aerospace or automotive, you've got metal materials, polymers, to very you're talking about surface roughness to microns, whereas we don't talk about those things in carrots and potatoes and chocolate. It's very different types of material. So you've got very different challenges. So really, when you look at online sensors, we're all aware of kind of process analytical technologies that came out of the pharma sector, and that was looking at very high precision, high accuracy lab equipment and trying to look at how we can move that into the factory. Whereas actually, you've got to look at it very differently in food and drink. And you've got to think about, what is the actual information I need? Is it about determining when a process is finished? Is it about determining some key material stream property in process so I can make a decision? But start with what you're trying to address first and look at developing a system that gives you that information to address that challenge. So when a process is finished, for example, instead of going down the high precision. Obviously, food and drink, we've got hygiene and food safety. So any sensor, really, we don't want this to be in contact with the food. It's got to be easy to clean. We don't want things like computers, electronics around if we don't have to. So again, Internet of Things, being able to stream data is very, very beneficial. And many manual operations as well. So in the robotic space, cobots is really, really interesting how they can work together in teams. So this is really the ingredients for successful intelligent sensing. And what I mean by intelligent sensing is taking a sensor measurement and using that to make a decision in a process. And then within food and drink, you really need to combine expertise in 4 areas. And so this is why I talk about humans in the loop. A lot of our projects, we start with this idea of, can we develop a closed control loop system, measure something, do an action? We've moved more towards, can we take a measurement? Within that measurement, can we do some analytics? And then can we pass that to a human to make a decision? So it's really looking at these technologies to augment humans, not replace them. But the skills you really need to be combined across 4 areas. You need to understand your material and your processes. And typically a food manufacturing organization, they'll have food scientists, they'll have chemical engineers. So they understand these 2. Then what happens when they want to go and invest in these digital technologies? They'll go to a sensor company who usually just provides a sensor. And then the missing part is often the data. Nowadays, you've got some sensor companies that will work with data scientists so they can do this part of it. Or if you're a larger food and drinks company, what they'll do is they'll maybe employ data scientists as well on the sensor company. But really, you need all 4 of these. And often when these 4 aren't working, this is when you have the problems, or you're not able to develop this. You'll see lots of sensor companies these days saying, "Oh, we're an AI company." Whereas if you look at the big AI and data companies, that's what they've got. You look at the Facebooks, the Amazon, they've got lots of data. It's usually our data, but that allows them to analyze it and create this insight. Whereas if you think about it within the manufacturing context, it's actually the manufacturers who've got the data once it's measured by the sensor. So there's some interesting work there. And I think some of the things we've learned over the years is that you need champions within an organization, and that's got to come from the factory floor to the boardroom. Because really, all these people are going to be using it, and they're stakeholders in the process and the company. So they've got to understand the technology and why we're doing this. This is just a bit of a methodology we've developed for one of our processes, and this is looking at how you take sensor data, combine it with machine learning to address a particular problem. So this is for resource efficiency. So this will be trying to reduce water, energy, waste within a process. And in our methodology, we've really split this into 3 areas. One is, what are you trying to address, which is in green, so the resource efficiency challenge. So first of all, you want to determine the KPI. So it might be how much energy is used, how much waste is created. Then you need to understand the requirement for the intelligent sensor. So that's, what is that piece of information? So it might actually be, if you're trying to reduce resource from, say, a mixing process, it might just be identify the endpoint of that mixing, or determine the optimal endpoint. Because once you think, if you're mixing for less time, you're naturally using less resources. It might be something to do with quality. It might be a key parameter on a food, such as moisture. That's something we look at a lot. Once you know what you want your intelligent sensor system to do, then you look at the sensor you need to use. That will give you that information. Then you need to go through the part of collecting your data, labeling the data if you're using I don't want to go into too much detail on the machine learning side, but we do a lot of supervised machine learning, so we need to label our data, and that's often more expensive and more troublesome than actually recording the data, and give some examples of that. The blue boxes are just your standard machine learning process. So design your models, so select the types of algorithms you want to use, how you're going to train them, do some feature engineering, so extract a feature from your sensor data, train your model, validate, adjust your hyperparameters, test your model, and then really just revisit that. Is that verifying resource efficiency? You can adapt this method and apply it for lots of other problems you're looking at, but this is the methodology we tend to use. First case study I'm going to talk about, and this is something we've been doing for several years now with several academic and industrial partners in the UK and overseas, and this is about self-optimizing clean in place. So for those of you who don't know what clean in place is, once if you've got a factory and you're making your food, or they use this for other things such as toothpaste and fast-moving consumer good product, what you've got to do is clean this. And this is like your dishwasher at home. So you put your dishes in, you press clean, and you'll have several different stages here. So the first stage would just be pumping through water, be rinsing off the loose fouling. Second stage would have some kind of detergent, some chemicals, typically caustic. Third stage, you're rinsing fluid through again to remove the chemicals, and you might have a fourth stage like sterilization. Now, if you think back to your dishwasher at home, every time you open that, your plates are clean, your glasses are clean, and that's really what you want. But stop and think about that for a second. You've been running that for maybe 2 hours. Were they clean in the last 30 seconds or the last minute, or were they clean after 5 minutes? Because if they were clean after 5 minutes, you've been paying for all that electricity and all that water to pump around your machine when your plates and your glasses are already clean. Now, that's not good for the environment, but you think of the size of your dishwasher at home and then think of the size of a dairy processing plant or a large-scale brewery. It's a huge problem. And the problem is that we don't have any insight. So actually, some dishwashers now do have some sensors in there that can look at the fouling, and they usually use conductance in the water, so it can switch between those different cycles. Well, that's what we're trying to do in this project. And it's a real big problem for the food sector, because what's happened over the years is this idea of mass customization. So the factory probably produces the same volume of product, but they're doing more smaller batches. One batch might have, say, for example, gluten-free, or it might have some premium ingredients in there. So they're making lots of smaller batches, and they need to clean between each batch. So the actual time they're cleaning the factory every day is more. So we came up with this project, self-optimizing clean in place. We've had a few Innovate UK funded projects through this, as well as the kind of more academic side of the work. What we've done is we've said, if you consider a factory, it's either a tanks or pipe works, and our tanks could be mixing vessels, they could be storage hoppers. Pipe work could be heat exchanger extruder, for example. So I've been working on the ultrasonic sensors on the pipe work, and my collaborator at Loughborough, Elliot Woolley, he's been looking at ultraviolet sensors in the tanks, and we've been looking at, can we collect the data, different conditions, and develop these predictive analytics to detect. And here for our intelligent sensor system, what we want to detect is they fouling in that piece of equipment, yes or no? So that's the requirement for our intelligent sensor system. We've done work at laboratory scale, very small benchtop rig, pilot scale or small pilot scale, and we've done some trials with industry partners, a variety of different applications. Unfortunately, we can't always show those results. A little bit about the ultrasound. So if you look on the left, we have the pipe, we have the orange represents the fouling, and we have the transducer at the bottom. We move over here, the transducer is going to send the sound wave through, and it's going to reflect from this interface between the fouling and the internal surface of the pipework. And all we're looking at is, and then it reflects back to the transducer. We record that sound wave that looks like something down here. And then what we do is we train this. So on a lab scale, we have a nice little open top, and we have a flat piece of stainless steel. We can put our fouling on it. We can flow through cleaning fluids and chemicals. And we've got that clear, and we've got a camera on top. So as we're recording our ultrasound, we can see if this is dirty or clean from the, I'll come back to it in a minute, from the camera. And then what we can do is we can label our ultrasonic signals as for either when it was dirty, when there was fouling there, or when it was clean, and then we can develop our supervised machine learning models. So this is binary classification. Is there fouling there, yes or no? And we've tried various different models, different ways of feature engineering, so some based on physical features such as reflection coefficient, received waveform energy, amplitude of windowed parts of the signal, or some using more the data approach, looking at the waveform as actually just a data set that we can go along and pick out the key features from there. And these are some of the results. So on the small lab rig, we had a piece of plate, we've got a camera above, and this black circle, this actually represents where the transducer is. So you're looking from above, you can see the fouling tomato in this case, there's a metal plate, and behind that there's the ultrasonic transducer. Now you're probably thinking, well, why do you need the ultrasound if you're just going to use the camera? And the reason behind that is because actually within a factory we can't use a camera. So what we've been doing in this work is training these intelligent sensor systems in our lab and then testing them in the factory where we're doing this idea around transfer learning, domain adaptation. It's really interesting. And what we can see here is some of our results. So on the top, we've got where it says from images. And what we can see is when it's orange, that means there's fouling there. And when it's blue, that means it's clean. So this is our labeled data, ground truth data. And what we can see is here is all these different algorithms we've run. So k-nearest neighbor, sport vector machines, random forest, adder boost. And we can see we get really good prediction accuracy, around 99%, except for this support vector machine. And this is one of the issues we find with machine learning is this idea of explainability. So it hasn't given us a very good result. It's predicting it's dirty by the orange lines when we know it's clean from the images. But why? This is one of the challenges we always have to get around with machine learning. On the bottom, at lower temperature, we found actually that works very well. I'm a little bit conscious of time, so I'm just going to skip through this one super quickly. This is mixing. And what we've done here is we've done some lab scale experiments, just honey and water, and we're trying to predict the end point of the mixing process using this. And we've actually, the other one we were using shallow machine learning algorithms, whereas this one we've gone to the more deep learning, so long short-term memory neural networks, convolution neural networks. And again here, we've also tried to do regression analysis where we've predicted the cleaning time. And what we've seen here is actually if you add multiple sensors, some of them perform well at the beginning of the mixing. So for example, this one, the blue line here, but then it goes off towards the end. And others are terrible towards the start, but then get better. And if we can combine them, we get this orange line, which is a better prediction. And this is just showing some of the work we've done on the transfer learning methods. I'm not going to go into this in detail, but transfer learning is really, really important for digital manufacturing, this type of area of sensors, because it, as I said, it allows us to train that model in the lab and then apply it to a factory setting. So if you went to a industrial partner and say, yeah, we've got this fantastic sensor, intelligent AI sensor technology, but we're going to have to spend the first 6 months actually collecting data from your process before we can get any benefits, that makes it difficult for them to get on board with that project. Whereas if you have your pre-built models because you've got data representing your problem, then it's a lot more easy to apply. You still need to do some checks in there, and we've got ways of doing that. So this is something we're really, really excited about. Final project is BrewNet, and this was actually a feasibility study funded by Connected F4.1. So this has been ourselves at Nottingham, University Leeds, who are on the IoT side, and a local brewery in Nottingham called Totally Brewed. And what we wanted to do is actually look at a really difficult sensing task, which is fermentation. Fermentation is a nightmare because you've got a 3-component system in there. You've got sugar dissolved in water, and then as you add your yeast, you get the fermentation, so it's producing ethanol. But you've also got lots of bubbles in there. You've got convective currents, everything flowing around. So it's really not easy from a sensor. And really, we want something that is cost effective and simple to use for the. So the brewery we worked with has 3 people working there. So there's only 2 people in the brewery. This is the kind of probe we built. I appreciate it doesn't look great, but we actually were putting this in the bottom of the fermentation vessel. So we built this into a tri-clamp port. We could put it in, and this would send a sound wave through a part of the actual wort, so that the fluid in there, and we could record that signal. And we play around with some different machine learning methods, and we looked at kind of linear regression, it's very simple, and artificial neural networks, Gaussian methods, and the actual value taken, because we were taking samples off as well, and we're measuring so with the fermentation, we wanted to determine the alcohol by volume, so we're tracking that process. And we could find we actually get fairly good predictions there. This graph on the right, what this is showing us is really about this data volume. So the more data we collect, the better the prediction. This is one of the challenges we find actually, because we were developing models for just one type of beer this brewery made, because we kind of thought we might need different models for different formulations. And this was a challenge because actually the beer they made the most, they only brewed it once every 2 months. So for us to get our 10 examples, we're talking about 2 years worth of data collection, not 2 years continuously, but 2 years before they got to about 10 batches. So that's something we really need to look at. But again, we've got some ideas with adjusting some of the features through these transfer learning methods that we can look at. But I think as well, I think everyone gets really excited about these digital manufacturing technologies. But what we're really interested in our group is looking at what are some of those challenges and just trying to address them, the challenges for adopting these technologies and just being realistic with them. I think that's really, really key. So final slide, because I think we're running out of time. Low costing process, ultrasonic sensors, machine learning, they can effectively monitor industrial processes, but there's still challenges around there, around data interpretability, explainability, trust, bias is a big challenge, a lot of data sets. I always think humans in the loop is key. We've got to look at these autonomous technologies to augment humans, not replace them. And there is some challenges there, data labeling, data collection, and lots of acknowledgements, because these have all been collaborative projects, industry and academia, and some of the publications. If you want to find out more about any of these, just feel free to get in touch, send me an email. So that's it for us. So I think we've got a few minutes for questions. Is that right, Tom?
Yeah, thanks for that. Yeah, there's maybe just a minute or so before we move into the panel discussion. So before I just ask you the odd question that's popped up in the chat, for all of the speakers joining us in the panel discussion, this is your sort of call to get ready to answer some questions. If you can, if you're happy to share your camera again, that would be great. But if you can stay on mute until you're particularly answering a question, that will help with sound quality and sort of and bandwidth. And then of course you can also use the blue hand to call. But while people are doing that, yeah, there's a couple of questions, Nick and Deborah. So the first one that's in the chat is, it's amazing you're able to detect fouling from milligrams of fouling on top of hundreds of grams of steel. Presumably it needs regular recalibration to cope with slight changes in conditions of the steel.
Yeah, it's actually a really good question, because when we started doing this work, so we're looking at physical fouling. That's probably one of the things I didn't go into in detail. So we've not gone down to the actual microgram kind of biofouling level, although there is some people doing similar work using similar technologies without the machine learning while looking at that. To get over the calibration task, this is why we've been doing using some of the machine learning approaches, because what we find is actually if we collect enough data, because one of the challenges you first have is when you put the transducer on, it contacts differently each time. So you get a different, even for a clean pipe, you get a different recorded signal. But if you do that for enough different systems, then what happens, your model can generalize across that, because there tends to always be a difference when the fouling is there or not. So that was something we found, because we were very conscious at the start, do we actually need to use machine learning for this? We're interested in it from some other projects that we've been working on, but we were kind of like, actually, are we just doing this because it's a cool thing to do? Why don't we just look at the reflected signal amplitude, which tends to jump up once you've got a clean pipe? But actually, when we started doing more and more experiments, we were finding, recalibration of the transducer, contact, also temperature. Ultrasound is very temperature dependent. We found there was a real big problem there. And if we just looked at, for example, the amplitude, it wasn't working very well. Gradients is a really good thing to put on. But yeah, that's what we found. This is actually one of the papers you'll find. We've just tried to look at this for one type of fouling and build a model for that. And then we built a model where we've combined all the different types of fouling. And again, the more data you get, the better across the wider range of temperature and different transducer contacts, the better your model can generalize. So we've done quite a bit of work in that. Yeah, great question though. Good start.
Yeah. And the final question, sort of specifically, Nick, on your talk, what problems did you encounter when trying to determine the end mix for honey/water? When is it mixed enough, and who or what determines that criteria?
Yeah, so I guess for that one, we were playing around with different problems we look at. So mixing is kind of one of the problems that some of our industry partners in the food have said, oh, we'd love to be able to monitor that. And we initially started looking at dough mixing, but it's not really the right problem to look at, because again, that transducer is measuring what's happening at that internal surface, and obviously with dough you've got big ball moving around and impacting it, so it wasn't a great one. So we decided on honey and water. We determined it was mixed based on, so again we had a camera looking at it when we believe, and we did some image analysis with one of our collaborators, and when we determined there was not any variation in the image, but that's when we determined it was fully mixed by that. The kind of problems we had with the actual sensors were the kind of contact in them. With the steel plates, we use kind of magnetic transducers, and actually with the ultrasound, we found with the ultrasound, when we started, we were using transducers at about £1,000, £2,000, but we found we can actually get them to work just as well with ones that are about £20. So we just glue them on. So we don't care if we glue them on a glass vessel, it doesn't really work that well. But we were having some problems with the transducers kind of rocking a bit at start before we glued them on. That was kind of the issue.